Welcome back to the Deep Dive, where we plunge into the fascinating knowledge tucked away in the sources you share with us.
Great to be here.
Today, we're turning our attention out into space to an asteroid known as 7 Iris.
Number 7.
Number 7, yeah. And the name itself is pretty captivating, isn't it, Iris?
It is. It immediately brings things to mind.
Like a vibrant rainbow, maybe, stretching across the sky, or perhaps that swift messenger goddess from, ancient Greek mythology.
Right.
How could that kind of beautiful imagery connect to, well, a chunk of rock floating out there between the planets?
It does make you wonder, and the sources you've given us, they really offer a rich tapestry to explore exactly that connection. It seems asteroid 7 Iris is, well, far more than just its number might suggest.
Exactly. So this deep dive is our chance to go beyond just the label, the number, and really understand what makes this specific asteroid living out there in the main belt between Mars and Jupiter, what makes it noteworthy.
And we've got quite a stack of material here.
We do, covering everything from, its initial discovery and that really evocative mythological name, all the way through to its physical characteristics. What radar's shown us about its surface, which is surprisingly complex, actually. And then there's a truly unexpected recent finding about its composition. Water, believe it or not.
That one's a biggie.
Yeah. And even the kind of chaotic cosmic neighborhood it lives in terms of how things spin and tumble out there.
So our mission today basically is to pull out the most important bits from these sources. The surprising facts, the aha moments.
The key insights.
Exactly. And bring them to you so you can feel like you really get this one significant piece of our, well, vast and dynamic solar system.
Okay, let's embark on this journey then. The story of Iris. Starting right at the beginning, its discovery.
Right. So the story of finding asteroid 7 Iris. It starts back in the 19th century. It was first spotted by an English astronomer, John R. Hind.
And the date was August 13th, 1847, so quite a while ago now.
It really was.
Yeah.
And he made this discovery from his observatory in London, which, as you said, was a serious achievement for that time. Using the telescopes they had back then.
Yeah, it must have been tough.
Identifying these faint, moving points of light against the stars, it took real skill, real patience. And according to our source, Iris was especially important for Hind because it was actually his first asteroid discovery.
Ah, his first one. So a landmark moment for him.
Definitely. Both for his career and just, for the whole effort of mapping these things in our solar system.
A very personal connection for him right there. And he chose the name Iris. We touched on the mythology, but let's really unpack that. Who was Iris in the myths?
So in Greco-Roman mythology, Iris is, well, most famously the goddess of the rainbow. That visual link is immediate, right?
Yeah.
Powerful.
Yeah, absolutely.
But her main job, and maybe the more significant one when you think about connection and bridging distances, was as a messenger of the gods.
Like a divine courier service. Olympus to Earth.
Pretty much, yeah. She was one of the key links for divine communication. And the source points out she wasn't just any messenger. She had this special, trusted role as the personal messenger of Hera Juno in Roman myth, the queen of the gods.
Okay, so she had direct access.
Yeah.
Influence. A hotline to the boss, basically.
Exactly. That adds some weight to her role.
Is there a specific myth that kind of shows her in action as a messenger, something that ties into these ideas of connection we might look for?
Yes. One source brings up the famous story of the voyage of the Argo. Jason and the Argonauts, quest for the Golden Fleece.
Right, got it.
Within that big story, there's the smaller part about the blind prophet, Phineas. He's being tormented by the harpies, those nasty bird women creatures.
Harpies. Yeah, I remember them. Not pleasant company. Very messy.
Exactly. And they were making Phineas's life miserable, swooping down, stealing his food, fouling up his house. And this torment, it was actually a punishment from the gods.
Why? What did he do?
Apparently, he'd been a bit too free with his prophetic gift. He was revealing too much of the gods' will to mortals. Spilling divine secrets, basically.
Ah, okay. Punishment for loose lips. Divine edition.
You could say that. And it's here that Iris steps in. The Argonauts are trying to help Phineas, maybe drive off or even kill the harpies. And then Iris appears. She delivers a message straight from the gods.
What did she say?
She tells Castor and Polydeuces, two of the heroes on the Argo, not to kill the harpies. But instead, she makes a promise. The gods themselves will lift the curse from Phineas.
Ah, okay. So she brings a message that stops potential violence and offers, well, hope, an end to his suffering.
That's the key takeaway from this particular story. Iris acts as the bridge between gods and mortals, between the heroes and the tormented prophet. She brings information that changes the whole situation, offers a path forward. She really embodies that idea of communication, intervention, delivering crucial news, often with this sense of hope or a turning point.
So, right from its name, the mythology behind it, this asteroid carries this really powerful association with messages, bridges, hope, divine connection. It's way richer than just a random number.
It absolutely is. And one of your sources really dives into how this name, Iris, and the whole concept of the rainbow have sort of echoed and popped up in all sorts of different, sometimes unexpected places in human culture and thinking.
Okay, let's explore that. Where else does this iris or rainbow theme show up? Things maybe not obviously linked to an asteroid or the myth.
Well, starting in nature, there's the flower, the iris. Beautiful flower. The source even notes, fun fact, it's the state flower of Tennessee.
Huh, okay.
Then moving to, well, us, the human body, the color part of your eye, that's called the iris too,
Right.
controls the light coming in. And building on that, there's this practice called iridology.
Iridology.
Yeah, it involves examining the patterns and colors in the eye's iris with the belief, and it's the belief system that it can tell you things about a person's physical health, maybe even their personality.
Wow. So the name links to something in space, a flower, and part of our own bodies. That's already quite a reach.
It is. The source also points to organized groups, even subcultures, that have picked up these names or symbols, like the Order of the Rainbow for adolescent girls, which has ties to the Freemasons. The source describes their rituals and symbols as, quote, quite genteel, very Hera, or Juno-like.
Directly linking back to the goddess Iris served.
Exactly. Then, on a much darker note, the source mentions, starkly, the completely unrelated and unfortunate use of the identical name for a group linked to Charles Manson. Just highlights how potent symbols can be twisted, or how names can coincide in grim ways.
Yeah, that's quite a jarring contrast. Any other groups?
There's also the more modern sort of migrant neo-hippie group called the Rainbow Family, known for large gatherings, counterculture stuff, and even in music there was a British heavy metal band, now defunct, called Rainbow. The source suggests they had a sort of medieval troubadour aura, maybe hinting back at old stories, journeys like the Argo.
So the name touches nature, biology, fraternal groups, counterculture, heavy metal. It's a name that clearly clicks with very different parts of human life.
And the symbol itself, the rainbow, carries just huge meaning across cultures and time. Like the
Yes.
source highlights, in the Bible, Genesis, after the flood, the rainbow is this massive symbol of hope, God's promise, the covenant, not to destroy humanity that way again.
A symbol of hope.
Yeah. Then in classic poetry, it's often used to symbolize mutability, changeableness, or even the diversity, the sheer variety of the human species. And of course, today, it's widely known as the symbol of LGBTQ plus pride, representing diversity, inclusion, and also a symbol linked to the hippie movement, peace, love, harmony.
Hope, diversity, change, promises, inclusion,
Right.
all packed into that one visual. You can see why the name has such sticking power.
You really can. And then shifting into a different kind of interpretation, one source looks at potential astrological meanings.
Yeah.
What associations does asteroid Seva Iris have within that practice?
Okay, astrological context.
Yeah.
What are the core ideas there?
Well, they seem to revolve around that original messenger role. Things like bearing messages, acting as a bridge, a go-between, making connections, facilitating communication, storytelling, even related ideas like archives or revealing hidden things, seeing something as a key factor, or representing passages.
Okay, those fit pretty well with the myth, but the source lists some less obvious ones too, right?
It does, yeah. It includes more abstract things.
Yeah.
Like fragile hope or idealism. That idea of mutability, changeability comes up again. Connections to liberalism, pluralism, tolerance, the ability to live with ambiguity, embrace diversity. It also mentions sympathy towards gayness or bisexuality, a kind of general hippie ethos, and even traits like naivete, openness, chasing dreams.
It's quite a mix, linking practical communication to these broader social and emotional ideas.
And there are even more specific links drawn, like to photography and the media in general. Interestingly, the source also links it to feelings of being watched, observed, stalked, feeling under the microscope, and also restlessness.
That under the microscope idea, it does kind of echo the iridology link, examining the eye's iris. It's like the name itself builds these bridges between totally different concepts.
Exactly. The source even links it to things outside traditional planetary astrology, like the Sabian symbol for Chiron's discovery degree, which is pot of gold at the end of the rainbow. Rudhere's interpretation, cited there, talks about a covenant between man and God, transubstantiation, linking different things in harmony. Very much that bridge idea again.
The Rainbow Bridge.
Yeah, that phrase is mentioned too, used in some spiritual context for the connection between the divine, the higher self, and the everyday personality.
So Iris isn't just a messenger in this view, but maybe represents these deeper links between different levels of reality or consciousness?
That's the interpretation the source offers, yeah. It explicitly calls Iris a female Hermes figure, drawing that direct parallel with the male messenger god. And the source gives a couple of quick examples from astrological charts to show how these ideas get applied.
Like the one about Christopher Reeve.
Yes. In his chart, apparently Iris was exactly conjunct his sun. The interpretations drawn connect this to his, quote, gentle personality, like Clark Kent, and then, more tragically, to the idea of a tiny thread joining his earth, his body, with his heaven, his head, a connection obviously severed by his accident. It uses Iris's symbolism of a vital link, a bridge, to frame his story.
Wow. That's, yeah, a powerful interpretation. Moving.
Another example given is Hugh Hefner. Here, the source links the asteroid Estrella to the playmates, and Iris to the iris of the camera lens, the glaring photographic lens. It makes that link between the asteroid name and the physical part of the camera, or the eye. Notes that it's not from the myth, but still seen as significant in this interpretive way, and it calls these Mother Earth asteroid nuances different from, say, centaur symbolism.
So from photography and being watched to symbols of diversity and hope, the name Iris clearly sparks a huge range of interpretations. It's fascinating how a name given to a rock in space can echo through so many different parts of human culture and thought.
It really is. Shows how we project meaning onto the cosmos, doesn't it?
Okay, let's shift gears now. Moving away from the symbolic meaning of the name, let's bring it back down to the physical reality. Where does asteroid 7 Iris actually live in our solar system? We said the main asteroid belt.
Right. The main belt. That's the region between the orbits of Mars and Jupiter. Our sources call it the smallest and innermost circumstellar disk in the solar system.
Okay, so smaller and closer in than, say, the Kuiper belt or the Oort cloud way out there.
Exactly. Now, how did the belt get there? The old idea, a planet blew up. It's definitely not right, according to modern science, and your sources are clear on that.
Right, that's debunked.
The belt formed from planetesimals, the building blocks of planets, from the original cloud of gas and dust that made our solar system.
So they were trying to become a planet.
That was the plan, yeah.
Yeah.
But Jupiter, huge gravity plate spoiler. Its gravitational nudges, its perturbations, gave these planetesimals way too much kinetic energy. So when they collided, instead of gently sticking together, accreting into something bigger.
They smash each other apart.
Pretty much. Jupiter turned the construction site into a demolition derby. And this chaotic process meant a huge amount of mass got lost from this region. Our sources estimate something like 99.9% of the belt's original mass was ejected within the first 100 million years or so.
99.9%. That's staggering. So what's left is just a tiny, tiny fraction of what was there.
Exactly. The total mass of the entire asteroid belt today, it's estimated to be only about 3% of the mass of our moon.
3% of the moon. That really drives home how much got thrown out.
It does. And even that little bit of remaining mass is mostly tied up in just a few big objects. Sources say roughly 60% of the belt's total mass is in the four largest series. Now, a dwarf planet, the biggest, about 950 kilometers across. It's like 39% of the total mass right there.
Wow.
Then Vesta, Pallas, and Hygeia. They're all under 600 kilometers.
So Iris is smaller than those big four. How big is it, roughly?
Iris is still considered one of the larger asteroids, but yeah, definitely smaller than that top group. Its average diameter is around 241 kilometers. Sources also give more detailed shape estimates, approximating it as a kind of stretched sphere, an ellipsoid, with dimensions roughly 268 by 234 by 180 kilometers. So not perfectly round, but substantial.
Okay, still hundreds of kilometers across. What about its mass and density? How heavy is it for its size?
Yeah, this is where things get a bit fuzzy, as our sources show. Different techniques, different models, they give slightly different answers. Estimates for Iris's mass range from about 7.24 times 10 to the 18 kilograms, up to a higher estimate, maybe 3.98 times 10 to the 19 kilograms.
That's quite a range.
It is. These numbers come from analyzing how its gravity bends the path of spacecraft, or from really precise tracking data, the ephemeris data. And each method has its uncertainties. So naturally, the density estimates, which you calculate from mass and size, also vary depending on which numbers you use.
So scientists are still kind of zeroing in on its exact weight and how tightly packed its material is.
That's right. The science is always improving, refining these numbers as we get better data, better techniques. Now, besides size and mass, the asteroids in the belt aren't all the same stuff. There's a definite compositional gradient.
A gradient, like they change depending on how far out from the sun they are.
Exactly that. Asteroids get classified into different types based on their spectra. The light they reflect tells us about their surface material. The main types are carbonaceous, C-type, silicate, S-type, metal-rich, M-type, and so others. And the general trend is that S-types, then C, P, and D types, are found further and further out from the sun.
Okay, and where does Iris fit in that lineup?
Iris is an S-type, silicate-rich. These types are more common in the inner part of the main belt, usually closer than about 2.5 astronomical units from the sun. Their spectra show silicates, some metal, but crucially not much in the way of carbonaceous compounds like you find in C-types.
What does that lack of carbon stuff suggest?
It suggests the material in S-types has been, well, processed, modified from its original state, probably through heating in the early solar system, maybe even melting and reforming. S-types also tend to be brighter, have a higher albedo, reflect more light than the darker C-types. They make up a good chunk of the belt's population, maybe 17% or so.
So Iris is basically a stony, processed asteroid found in the inner, hotter part of the belt, one of the larger ones, but much smaller than the giants. And it lives in a belt that lost almost everything and is surprisingly empty.
That sums it up pretty well. And yeah, that idea of the belt being this crowded, dangerous place, like in Star Wars.
Yeah, exactly.
Totally wrong. The average distance between asteroids is huge, about 965,000 kilometers, 600,000 miles. You could fly spacecraft through there many, many times and probably hit nothing. Pioneer 10 did it first, back in '72. Lots of missions have gone through safely since, or even orbited asteroids like Ceres and Vesta.
Okay, so the popular image is just way off. It's more like navigating a vast, incredibly sparse collection of rocks.
Like a cosmic archipelago, maybe, rather than a dense minefield. And to really understand those objects, to see what they actually look like, not just as points of light. We need more than just regular telescopes.
Right. Optical telescopes give us size, brightness, maybe rotation from how the light changes, but to see the actual shape, surface features.
That's where radar imaging comes in. You bounce radio waves off the asteroid, listen for the echo. Analyzing the timing, the delay, and the frequency shift, the Doppler shift of that returning signal lets you build up a picture of the object's shape, its topography. But it's tough for main belt asteroids like Iris.
Why? Why is it harder for objects further out?
Well, the radar echo gets incredibly faint with distance. It follows an inverse fourth power law. That means if you double the distance, the signal you get back is 16 times weaker. So echoes from main belt asteroids are just way, way weaker than from near-Earth asteroids that swing much closer to us.
So you need a really powerful radar and kind of perfect timing.
Exactly. Huge transmitter, super sensitive receiver, and ideally, you want the asteroid to be as close as it gets in its orbit. And one of the best chances came in November 2006. Iris made a relatively close approach, 0.85 astronomical units. That gave the best main belt asteroid radar opportunity anyone had had up to that point. Got really high signal-to-noise ratios, around 500. Excellent signal.
Okay, sounds like a golden opportunity to get a good look. What did they do? What kind of observations?
They used the Arecibo Observatory in Puerto Rico, which had that amazing radar capability, sadly no longer with us. They did multiple transmit-receive cycles using a specific kind of signal, 2380 megahertz, circularly polarized. And a key technique they used, highlighted in the sources, was something called a long code.
A long code. What's
Yeah.
special about that?
Okay, think of it like this. With big, distant objects like main belt asteroids, the radar echo can get spread out a lot, both in time delay, distance, and Doppler shift, speed due to rotation. If you just use a simple, repeating radar pulse, the echoes from different parts of the asteroid can overlap in confusing ways. It's called aliasing. Makes it impossible to sort out which signal came from where.
Like signal traffic jam.
Kind of, yeah. So the long code fixes that. Instead of a simple repeating pulse, it uses this complex non-repeating pattern. This lets the scientists decode the echo from each specific delay and Doppler spot uniquely. It separates the signals, avoids that aliasing confusion, gets you a much clearer picture. The downside is it takes a lot more computer power and time to process the data.
Okay, so a necessary complication to get a clear view of these distant, complex targets. And this gives them delay Doppler images. What do those actually look like? How do they show the shape?
Right? In a delay Doppler image, one axis is time delay, how long the echo took to come back, which tells you distance. Longer delay, further away part of the asteroid. The other axis is Doppler shift, how the frequency changed, which tells you the velocity of that part towards or away from you due to rotation. Now, if you were looking at a perfectly smooth rotating sphere, you'd see a very simple, predictable shape in that image, like a smooth, concave downward curve.
So anything different from that smooth curve means the asteroid isn't smooth.
Exactly. If you see structure inside that main echo boundary, especially echoes showing up behind the leading edge, the closest part of the asteroid that's a dead giveaway for complex topography, it means there are parts of the surface curving inwards, dips, valleys, concavities, instead of just presenting a smooth, convex face to the radar.
Okay, structure behind the front edge means bumps or holes or craters. What did the 2006 Arecibo data specifically show about Iris's surface?
Well, the data help refine its overall shape, confirmed it's roughly that ellipsoidal shape with the dimensions we mentioned. But the really key finding from the radar images was that Iris is definitely topographically complex. It's not just a smooth space potato.
Could they pick out specific features?
Yes. Now, the view they got was mainly of the high southern latitudes on Iris. The subradar point, the spot directly facing the radar, stayed down around -48 to -50 degrees latitude during the observations. But in that visible southern region, the images revealed three pretty obvious concavities.
Concavities, like dense.
Yeah, basically, denser depressions. They estimated these were each roughly 50 kilometers across, and they seemed almost equally spaced in longitude around the asteroid's south pole. The scientists concluded these are probably large impact craters.
Three probable 50-kilometer craters just in the southern hemisphere view. That paints the picture of a significantly battered surface. But you said the view was limited to the south. How much did they actually see well?
And that's a major caveat, a limitation of this dataset, as the sources really stress. They only got a good, clear look at that band of southern latitudes, the northern hemisphere. Largely unseen, or at least not seen at an angle where you could reliably map features. To get a full, unambiguous 3D shape model from radar, you really need to see more of the asteroid rotate, and you need coverage extending much closer to the equator, maybe 20 degrees latitude or more. This observation just didn't have that.
So the parts of their shape model showing the northern hemisphere, they're not really based on direct radar data.
Pretty much. The topography shown in the model for those unseen northern parts is more of an artifact of the mathematical fitting process they used. It's filling in the gaps based on the southern data and the assumption of an overall shape, not a direct map of what's actually there.
Okay. Were there other limitations, uncertainties in the radar results?
Yeah, a few. The source mentions that the precise way radar waves scatter off the surface, they call it the angular scattering law, is kind of tangled up with other factors in the modeling. This limits how precisely they could pin down the asteroid's exact dimensions and the exact direction its spin pole is pointing. Also, they were deliberately conservative in their modeling. They used weighting techniques to avoid showing features that might just be noise or artifacts from the computer algorithm, which is good, means the features they did show are probably real. But it also means they might have underestimated or smoothed out the most severe parts of Iris's actual topography. Things that might be hinted at in the raw data, but didn't make it into the final cautious model.
So the published model might be a slightly gentler version of the real Iris.
That's a possibility the authors themselves raise. They point to these strong, brief, bright spots, glints, that pop up in the radar images. These had actually been seen in earlier, less detailed radar views of Iris back in 1984 too, though from different spots on the surface because the viewing angle was different. And these glints often aren't reproduced well by the shape models.
Why not?
Could be a couple of reasons. Maybe different parts of Iris's surface just scatter radar differently. The scattering law isn't uniform. Or maybe the topography in those specific glinting areas is just too extreme, too rugged, too complex for even their sophisticated but conservative modeling to capture accurately.
So even with this fantastic 2006 dataset, Iris still keeps some secrets about its exact shape and its roughest features.
It certainly does, especially for the parts we couldn't see well, or features that maybe push the limits of the modeling. But the authors draw a really interesting conclusion from what they could see about Iris's shape and complexity. They suggest that based on its general regularity, but also the size of its features relative to its overall size, the fractional relief iris represents a plausible transitional object.
Transitional. Between what and what?
Between two main types of asteroid shapes. On one end, you have the smaller asteroids, say less than 50 kilometers across. They often look really irregular, lumpy, very non-convex. And they can have huge concavities, like craters or gouges, that are enormous compared to the asteroid's tiny size.
Okay, the little lumpy ones.
Right. Then on the other end, you have the really big guys, over 500 kilometers, like Ceres and Vesta. They tend to be much more regular, almost spherical or ellipsoidal, nearly convex. They generally lack those kinds of disproportionately massive craters or concavities.
So Iris, at around 240 kilometers, is kind of in the middle. Big enough to be somewhat regular, unlike the smallest ones, but still showing those big 50-kilometer probable craters. It links the two extremes.
Exactly. It seems to show that progression, how impact history and just sheer scale influence the shapes we see. They contrast Iris with 216 Cleopatra, another main belt asteroid imaged by radar. Cleopatra has that crazy extreme dog bone shape, very non-convex.
Yeah.
But paradoxically, its extreme shape actually made it easier to figure out its overall form from limited radar data. Iris, being less dramatically weird, makes that global reconstruction harder without seeing it from more angles.
Huh. Fascinating how the object itself changes the challenge of seeing it. Okay, so radar gives us this picture of a substantial cratered world. But maybe the most surprising recent finding about Iris touches on something even more fundamental, its composition. Specifically, water.
Yes. This is a huge deal, reported just recently, February 2024, and it directly challenges some really long-held ideas about S-type asteroids. This is the first direct observation of water molecules on the surface of an S-type asteroid, and 7 Iris was one of the 2 where they found it.
On an S-type. Hang on, didn't we just say S-types are the stony ones? From the inner belt, thought to be born dry because it was too hot for water ice when they formed?
That is precisely why this discovery is so unexpected and so important. The standard picture, is that S-types should be basically anhydrous without water because they formed in the hotter inner part of the solar nebula. Finding water there directly really shakes things up.
Okay, this is a genuine surprise then. How did they find it? How do you detect water molecules from Earth or near Earth? What instrument?
The detection came from SOFIA. That's the Stratospheric Observatory for Infrared Astronomy. A really unique piece of kit, a 2.7-meter infrared telescope mounted inside a modified Boeing 747 SP airplane.
A telescope flying on a plane. How high up?
It flew way up there, about 13 kilometers, around 43,000 feet. High enough to get above almost all the water vapor in Earth's atmosphere, which blocks a lot of the infrared light from space that astronomers want to see.
Yeah.
SOFIA, sadly, flew its last mission in 2022, but the data it collected is still producing amazing results like this one.
And how did SOFIA actually pinpoint water?
They looked for a very specific signal, a fingerprint, in the mid-infrared light spectrum at a wavelength of 6.1 microns. The sources are very clear. This particular signal is produced only by the chemical bond of water molecules, H2O. Nothing else makes it.
Ah, so it's unambiguous.
Exactly. SOFIA had actually used this same 6.1 micron signature before to confirm water on the sunlit surface of our moon.
Yeah.
So it's a tried and tested, reliable method. So the team pointed SOFIA at 4 S-type asteroids. These 4 had previously shown a more ambiguous signal around 3 microns, which could be either water, H2O, or hydroxyl, OH. But using the specific 6.1 micron detector, SOFIA got a clear, definitive signal of water molecules from 2 of them, 7 Iris and 20 Massalia. The other 2 asteroids were just too faint to get a good reading.
Wow. Water confirmed on Iris and Massalia. So
Right.
if the theory was they formed too hot to have water, where did it come from? How did it get there?
Great question. The sources lay out a couple of main possibilities. One is maybe the asteroids did actually form, with this water somehow locked away. Maybe absorbed onto silicate grains or chemically bound inside minerals, even in that hotter region. That would mean we need to tweak our understanding of how things condensed in the early solar system.
Okay, so maybe it was there all along. What's the other idea?
The other explanation, which seems quite plausible, is that the water was delivered to them after they formed, and the prime suspects for delivery, C-type asteroids.
Ah, the ones from the outer belt, the carbonaceous ones, the ones we think are water-rich.
Exactly those. C-types are mostly found further out in the asteroid belt, where it was colder, and they're believed to be loaded with ice and water. The idea is that Jupiter's gravity, besides messing up planet formation, could also have scattered some of these icy C-types inwards over millions, billions of years. These C-types could then crash into the S-types that live in the inner belt.
So, impacts. Little icy asteroids from the outer belt basically rain down water onto bigger stony asteroids like Iris in the inner belt.
That's the proposed mechanism, yeah. Water delivered by impact from water-rich projectiles. And it fits nicely with that compositional gradient we talked about. The S-types are closer in, where it was notionally drier, C-types further out where it was icier. This delivery idea provides a way for water to end up on an S-type even if it didn't form with any.
That makes a lot of sense, actually. A vivid picture. How much water were we talking about? Did they find, like, hidden oceans or something?
No, nothing like that. The amounts detected were small, similar to what's been found on the moon, actually, roughly equivalent to maybe 1/3 of a liter of water. like a small water bottle spread throughout a cubic meter of the loose surface material, the regolith.
Regolith, that's the surface dust and gravity.
Yeah, the broken up surface layer.
Yeah.
So definitely not oceans, but water molecules clearly present in that top layer. Now, the exact form it's in, is it just sticking to the surface of grains adsorbed? Or is it actually part of the mineral structure, chemically bound? That's still an open question from this observation.
Okay, small amounts, but undeniably there. Now, with SOFIA retired, how are scientists following up on this? Is the search paused?
Oh, no, not at all. The search continues big time. Scientists are now using the James Webb Space Telescope, JWST, for this kind of work. It's expected to be sensitive enough to see that same specific 6.1 micron water signature. And actually, a key next step, according to the source, is to use JWST to confirm water on C-type asteroids using this specific signal.
Wait, to confirm water on the C-types, the ones we already thought were wet?
Well, yes, we presume C-types are water-rich, based on their overall composition and where they formed. But getting that definitive 6.1 micron spectral fingerprint directly from them is still needed for solid confirmation. It nails it down.
Okay. Get the smoking gun signal from the prime suspects, too?
Exactly. They're observing C-types like 142 Polana and 225 Henrietta with JWST right now, or the data is being analyzed. And this whole line of research, finding water on asteroids, it has implications way beyond just the asteroids themselves.
You mean for understanding where Earth's water came from?
That's exactly it. The leading theory is that a lot of Earth's ocean water was delivered by impacts early in its history. Comets were the early favorites, but often their water composition, specifically the deuterium to hydrogen ratio, doesn't quite match Earth's water. That puts C-type asteroids front and center as likely water carriers.
Right.
But now, finding water confirmed on S-types like Iris, it throws another player into the mix. Maybe even these inner-belt stony asteroids contributed some water to early Earth.
So, finding water on Iris could potentially add another piece to the puzzle of how Earth got its oceans, our own origin story.
That's definitely one of the exciting possibilities. Figuring out where water is located in the belt, what form it's in, how it got there. It's all directly relevant to understanding how water was delivered throughout the inner solar system, including here. It really shows how these seemingly small discoveries about distant rocks can connect right back to us.
It really underscores how interconnected the solar system's history is. Okay, so we've covered its name, its place, its surface, the surprise water discovery. The last big piece our sources get into is the complex dynamics of its environment, specifically how asteroids like Iris spin and tumble over time.
Ah, yes, asteroid spin. It sounds simple, but it's surprisingly complicated. Asteroids are constantly being influenced by different forces, and how they rotate can change quite dramatically over cosmic timescales. Understanding that evolution is tricky because asteroids are also different shape, orbit, history.
What are the main things that mess with an asteroid spin?
Broadly, there are two main types of forces involved: gravitational torques and non-gravitational torques. Gravitational ones come from the pull of the planets, especially big ones like Jupiter. Non-gravitational ones are usually thermal effects, like the YORP effect.
Okay, let's take gravity first. How does gravity affect spin?
Well, our sources explain that gravitational torques can really influence an asteroid's spin history, especially for asteroids like Iris in the inner main belt that have prograde rotation, meaning they spin the same direction they orbit the sun. This happens through interactions called secular spin-orbit resonances.
Spin-orbit resonances. Okay, what does that mean in, simpler terms?
Think of it like pushing a kid on a swing. If you push at just the right moment in the swing cycle, you build up energy, make it go higher. Similarly, if the rate at which an asteroid's spin axis wobbles its precession rate, or maybe even its rotation speed itself, happens to line up in a specific mathematical ratio with certain frequencies related to the planet's orbits and their gravitational pull, it can get a steady nudge, a torque, that significantly changes its spin state over time.
A gravitational nudge?
Yeah, and in the inner main belt, there are apparently lots of these secular spin-orbit resonances, and they overlap. Prograde rotators, spinning forward, are particularly likely to get caught in or pushed around by these resonances. Retrograde rotators spinning backwards relative to their orbit seem less affected by these specific resonances. Their tilt changes tend to be more regular, driven by simpler precession.
Okay, and what happens when these prograde asteroids in the inner belt get caught up in these resonances? What's the result?
The really key outcome, highlighted in the source, is that these gravitational torques and resonances can make the asteroid's spin axis orientation, its obliquity, its tilt, vary wildly, even chaotically, and it can happen over time scales that are relatively short, astronomically speaking, like maybe changes over periods of around 1 million years.
A million years still sounds long, but yeah, for changing the tilt of a whole asteroid, that's actually pretty quick.
What about the other forces you mentioned? Non-gravitational, your RP.
Right, the YORP effect stands for Yarkovsky-O'Keefe-Radzievskii-Paddock effect. Bit of a mouthful.
It's a thermal torque. Basically, an asteroid absorbs sunlight, heats up, and then radiates that energy back into space as heat, as infrared light. Now, if the asteroid's shape is irregular or if different parts of its surface have different properties, it won't radiate that heat perfectly evenly in all directions.
Okay.
This uneven radiation creates a tiny, tiny net force, and more importantly, a tiny torque on the asteroid.
Like a miniature, incredibly weak rocket engine powered by sunlight and heat.
That's a pretty good way to think about it, yeah. And this tiny thermal torque, over long periods, can cause the asteroid's rotation rate to gradually speed up or slow down. It can also slowly change the tilt of its spin axis, the obliquity.
And who does your ORP affect most?
It's most effective, it drives the fastest spin changes for smaller asteroids,
Yeah.
typically ones with diameters less than about 40 kilometers or so. For bigger asteroids like Iris, the thermal YORP torques are generally much, much weaker compared to the gravitational torques from the planets.
Okay, so gravity drives the chaotic tilt changes for bigger inner belt objects, and YORP drives spin rate and tilt changes for smaller ones. What happens where they both might matter, or in that middle ground?
That's where it gets really messy.
Yeah.
For those smaller asteroids where YORP is significant, adding its effect on top of the gravitational torques makes predicting their spin evolution way more complex. How fast it spins becomes really tangled up with the history of how its tilt has changed over time. You get this complicated dance between the longer-term gravity effects and the very long-term gradual YORP effects.
The source uses examples from simulations of other asteroids to show this, right? Not Iris specifically, but similar ones.
Exactly. They look at objects like 951 Gaspra and 8 Flora, which are also in the inner belt, to understand the kinds of spin behavior that are possible there. For instance, simulations show Gaspra, which is fairly small, is in a highly chaotic rotation state.
Yeah.
Its spin axis tilt can just wander all over the place, unpredictably. Because its natural spin frequencies happen to overlap with some of those strong secular spin-orbit resonances, like the Techman 6 resonances, those gravitational resonances just keep kicking its tilt around randomly.
So the gravity chaos drives the tilt wobble.
Yeah. And interestingly, the source notes that when you add YORP into the simulations for Gaspra, its effect on the spin rate is less simple than you might think. Because the tilt is wobbling around so much due to gravity, the asteroid's spin axis doesn't stay pointed consistently in a direction where YORP can effectively speed it up or slow it down for long stretches. The gravitational chaos kind of interferes with YORP's ability to consistently change the spin rate.
Huh. That's counterintuitive. The gravitational chaos actually makes the thermal effect more complicated.
It really shows how complex these interactions are. And the source also points out that 8 Flora, which is much bigger than Gaspra, more similar in size range towards Iris, but also in the inner belt, shows similar chaotic obliquity wandering in simulations. Even though it's bigger, its orbit and a key parameter related to its precession rate are similar enough to Gaspra's that it also gets caught in that resonant chaos.
So the chaotic spin axis isn't just for the little guys.
Apparently not. It suggests that even larger asteroids in the inner belt, like Flora, and therefore potential like Iris too, can experience this chaotic wandering of their spin axis due to these gravitational resonances.
Okay, so summing that up for Iris. It's an inner main belt asteroid. It's probably too big for YORP to drastically change its spin rate super quickly, but it's likely subject to the same gravitational chaos that affects the tilt of other inner belt asteroids like Gaspra and Flora.
That seems to be the key implication, based on the dynamics of similar objects discussed in the source. While YORP might be a slower influence on Iris's rotation speed, its spin axis is probably getting tossed around by these complex gravitational torques and resonance overlaps. Its tilt could be wandering chaotically over millions of years. It's just part of the dynamic environment it inhabits.
So even if Iris isn't, tumbling end over end wildly, its north pole could be pointing in very different directions over long timescales. The source also brings up the Yarkovsky effect here. Really?
Yes, very related to YORP. The Yarkovsky effect is also a thermal force from that uneven heat radiation. But instead of primarily affecting the spin, it affects the asteroid's orbit. Specifically, it causes a slow, gradual change in its semi-major axis, its average distance from the sun. It makes the orbit slowly spiral inwards or outwards.
Okay, how does that link back to the complicated spin?
Well, Understanding the combined effects, gravity torques, YORP changing the spin, Yarkovsky changing the orbit, is really crucial for studying things like how asteroid families evolve. Those groups of asteroids thought to come from a single parent body breaking up.
Right.
Scientists estimate the ages of these families based on how much their orbits have spread out over time due to effects like Yarkovsky.
Right.
But if the asteroid's spin axis is chaotically wobbling around due to gravitational resonances, as we just discussed for prograde rotators in the inner belt, that means the strength and even the direction of the Yarkovsky effect can fluctuate unpredictably too.
Because the Yarkovsky effect depends on which way the asteroid is tilted and spinning.
Exactly. So the source notes that this added complexity from resonant spin dynamics means that age estimates for asteroid families in the inner belt, especially those based on simpler models that assume smooth Yarkovsky drift, might actually be slightly underestimated.
Yeah.
The real orbital spreading might be more jerky and less predictable.
So the way an asteroid like Iris spins, potentially chaotically, isn't just some isolated detail about its rotation. It actually feeds back into how we understand the history and ages of whole groups of asteroids in the belt.
Precisely. It's another layer of that interconnectedness within the solar system, how one rock spins influences its path, and that influences our understanding of the entire belt's evolution.
Wow. We have certainly taken a deep dive into the story of Asteroid 7 Iris today.
We really have. We started with that name, right? The layers of meaning. From ancient Greek myths of messengers and rainbows to all these surprising echoes in culture, symbolism, even things like iridology.
Then we placed it physically, out there in the main asteroid belt. Understood how that region is really just the leftover debris from failed planet formation thanks to Jupiter, and how Iris fits in as one of the bigger remnants in what's actually a very empty part of space.
We used radar, like virtual eyes, peering through the distance to see its shape. Revealed this complex surface, likely scarred by huge impact craters. Saw it as this interesting transitional object, bridging the gap between the really small, lumpy asteroids and the biggest, smoothest ones.
And then came that huge surprise finding, water. Actual water molecules detected directly on its surface, overturning the old idea that S-types like Iris had to be born dry, suggesting maybe water was delivered by impacts from icy bodies from the outer belt, which adds a whole new wrinkle to the story of where Earth's water came from.
Yeah, a potential new source. And finally, we dipped into the complex, maybe even chaotic dance of its spin, how gravity in these resonances can potentially make even its tilt wander over millions of years, highlighting just how dynamic its environment is and how that connects to the bigger picture of asteroid belt evolution.
It's absolutely clear from all this, Iris isn't just some random numbered rock. It's got this rich, multi-layered story, a complex physical reality, a surprising chemical makeup, and this dynamic existence shaped by these immense cosmic forces.
And exploring Iris, even just through the sources we looked at here, it really hammers home how much we're still learning about our own solar system. Every object, even one we've known about since 1847, holds unique clues about how everything around us came to be.
It really makes you think about how these different parts connect, doesn't it? Like, could that chaotic spin we were just talking about, Iris's tilt, possibly changing over millions of years, could that actually affect how that water ice might be stored or exposed on its surface over time?
That's a fantastic question.
If its tilt is constantly shifting, maybe different parts get more or less sunlight over long periods. Could that influence where water is stable or how it might move around?
That interplay is definitely something to consider. The dynamics, the rotation, and the composition, the water.
Yeah.
They're almost certainly linked in ways we're probably just starting to figure out. They aren't independent things.
And it just leaves you wondering, what other secrets are still hiding out there in the vastness of the asteroid belt? Secrets that might shed even more light on the history of our own planet, maybe revealing even more about the origin of the water that makes Earth, well, Earth.
The search definitely continues.
Yeah.
And every new piece of the puzzle, like what we've learned about Sev's Iris, just adds another fascinating chapter to that incredible ongoing story of exploring our solar system.
A perfect thought to leave you with for this deep dive. Thanks for joining us.
Thank you.